I typically wait a couple more minutes if that's okay, Divya, to wait.
Yeah, of course. Yeah, I understand. How's everything there?
Yeah, it's fine. I'm actually currently at Indian Institute of Science, Bangalore.
Okay.
But yeah, I came here a couple of days back. But yeah, Madras things are going fine. Our semester, we are into the third week of a semester now.
Okay.
And yeah, this is a full-blown back to offline semester. So
Awesome.
happy.
Okay.
Yeah.
On campus, that's good. Yeah, it's a whole different learning experience when everyone is together. So I'm really glad.
Correct. Yeah. So after a couple of years of online, I'm actually enjoying my offline classes. Yeah, maybe next time you can actually visit us and give a talk here as well.
Yeah. Oh yeah, I mean, I have plans to come to India, of course, and I will definitely contact you.
Oh, that'll be great. Yeah, that'll be great. You were finished in 2011 or 12 from here, Divya? I'm trying to remember.
12. I was 12, yeah.
Do you remember Navneet? Was he in your batch? Navneet,
he was a senior to me. Navneet Krishnan, right?
Correct. Yeah, he's a faculty here. I just met him.
Oh, you did?
Yeah.
He's a faculty.
He's a faculty at Indian Institute of Science now. Yeah.
Oh, okay. Got it. Nice. Yeah. Okay, I didn't know. Yeah, where he was. That's great. Great to hear. I actually followed his project, my BTech project. I
see. Okay.
I took up his project after he left. So yeah.
Nice. Okay. Cool. Okay, maybe we'll get going, Divya. It's a couple of minutes past now.
Okay.
Good evening and good afternoon or good morning, different parts of the world. Thank you for attending this SpaceTalks webinar by the ExTeM group at IITM. I'm very happy to host Dr. Divya Panchanathan's talk today. Divya is from Axiom Space, where she's the business development manager in the in-space manufacturing team. She focuses more on the materials and the physical science aspects in the low Earth orbit. She's our alumni, IIT Madras alumni, and she got her master's and PhD from MIT in the field of mechanical engineering, and her focus has been on interfacial science. Her academic and industrial projects span areas like aerosol filtration, microfabrication, droplet levitations, drag reductions, and catalytic coatings. And her doctoral work was featured among the top 3 Gallery of Fluid Motion winners at the APS division of Fluid Dynamics. And at Axiom Space, she seeks to leverage microgravity and the space environment to spur innovation in the materials and physical sciences. And Axiom Space is keen to partner with academic and industry as well. So with that short introduction, Divya, the floor is yours, and we look forward to hearing your talk.
Thank you, Professor Subaya, for the kind introduction. Good evening to everyone present on the call, and good morning and good afternoon to other parts of the world as well. I really thank the ExTeM team for hosting me in this webinar series. I'm really honored and excited to be back at my alma mater to give this exciting talk and for having this opportunity to interact with the students and faculty and the broader ExTeM community there. With that, I'd like to begin my talk. Thanks for everyone who's present here. I'd like to first start by asking you to imagine the future. Can you imagine a day when you can save lives using materials that have been derived from research in space? Can you imagine a day when you can apply for a job in the low Earth orbit after your graduation And finally, can you imagine the day when you can tell your son or daughter that they can be living and working in space one day? Well, that day is not very far off. Axiom Space is working to make this a reality, this dream a reality. Our vision is to build a thriving home in space that benefits every human everywhere. And the way we are doing it is by building the first commercial space station. Our eventual goal is to be able to build cities in space, but as a first step towards that, we need to build the Axiom station. We are taking a phased approach to building our space station. So as most of you might know, the International Space Station has been orbiting the Earth for around 22 years now. It is going to be retired at the end of this decade. We are leveraging that platform that is still out there to do private astronaut missions and research missions to the ISS during this first phase. Our second phase is going to be when we will be attaching our modules to the ISS, and will be assembling the station from 2024 to 2028. Post 2028, we will be able to detach from this International Space Station and become an independent free flyer and an independent operating commercial space station. So this phased approach allows us to develop different expertise through the different phases. The first phase, we would be developing expertise over demonstrating leadership in human spaceflight and doing research integration. In the second phase, we would be assembling our hardware in space. And the third phase, we would be an independent commercial space station with all the capabilities to support all different types of customers. Our station will be comprised of 4 modules. The first 2 modules are the habitation modules, mostly dedicated to astronaut quarters, but there'll also be some research capabilities on that. The third module is completely dedicated towards research and manufacturing. So imagine an orbital lab in space. And the final module is the power and life support systems, which will help in making an Axiom an independent space station. I'd like to show you a short video which shows where we are today and shows some of the capabilities we are developing. I hope you can.
Yeah, it's playing, but there's no audio, Divya. Yeah.
Sorry, can you hear it?
I'm not able to hear the audio. Yeah.
Oh, I see.
The video is playing, fine. Yeah.
Okay. Maybe there's a setting I can change here. Just see.
There's an option to include your computer audio or something like that.
Oh, I see. Okay, never mind. I mean, this video is also actually online, so you can view it. Okay. It's mainly just showing some of the capabilities that we're developing. I'll just show the first half of the video. It's more visual, and then I'll stop, and then I'll go to the next slide there. So this is the propulsion system that is being built. This is already part of the station that's being built in Thales, Alenia, and Italy. So 90% of the design is right now done. This shows a video of how the modules are going to be assembled on the International Space Station. Yeah, I'm going to stop here. Go next slide. Okay. Sorry about that. But this video is there online on the Axiom YouTube page. You can definitely go view it online. The summary is that we already are well underway in building the first module, designing and building the first module that is going up in 2024. It's currently undergoing its critical design review. This means is that 90% of the design is done before it's going to the manufacturing phase. So this is a standard that's used, standard milestone that's used in the aerospace industry. We are building the space station to support diverse markets, different types of customers, all the way from government agencies, individuals, researchers and manufacturers, media and entertainment, other space agencies, defense and satellite industry. And this is just the beginning. There's a lot more people who can then benefit from the space station as well, but this is where we are starting. We are already starting to seed some of these markets by doing private and professional astronaut missions. We did our first private astronaut mission, AX-1, in April 2022, where we flew. This is a historic mission. This was the very first time. It was all the 4 people that were flown to the ISS were through a private company, and they paid for their own travel. There's a lot of research that was done on that mission as well. We have lined up our second mission, AX-2, the record holder Peggy Whitson as the commander. We also have a number of professional astronaut missions. We are developing relations with countries to train and fly their professional astronauts, like the UAE, Italy, Hungary, New Zealand, etc. We also won the NASA spacesuit contract recently to build the next generation spacesuit along with another company. What this means is that we are also developing extravehicular capabilities in addition to the space station itself. I'd like to spend a little bit of time talking about the AX-1 mission, which was a huge success and a huge achievement of Axiom Space. Is the very first time a company is completely trained astronauts, sent them to space, managed the mission, and brought them back. There was a lot of research that was done on this mission as well. There was the Amazon Web Services edge compute demonstration. There was a payload from MIT that had a small prototype of self-assembling space structures. A payload from Technion Israel Institute of Technology, which was on making polymer lens using taking advantage of the microgravity environment. There was a first demonstration of two-way holoportation and some life science experiments from the Mayo Clinic as well. And in these astronauts not only brought research with them, but they also brought a lot of outreach and art activities like those shown here. There was a piano duet that was done live in space, an interview with the Children's Hospital of Montreal, and then the demonstration of a space duel that was specifically designed for shining in space in the microgravity environment. So as we're seeding the private and professional astronaut missions, we are also working towards in-space manufacturing applications, which is what the focus of today's talk is. The first question you may have is, why go to space for manufacturing? Well, there are three primary advantages of space environment: the microgravity environment, the unique vantage point, that is the orbit in which the space station will be, and then the extreme environment of space, that is the outside of the space station. The microgravity environment is very unique. You cannot generate it for long periods of time accurately on Earth. You need to go to space to get that microgravity environment for a long period. And this microgravity environment has multiple advantages like lack of convection, lack of sedimentation, and a few other effects that we'll talk about, which results it gives us advantages for creating advanced materials like optical fibers, nanomaterials, alloy crystals, and also in the life sciences, like regenerative medicine, 3D bioprinting, and synthetic biology. You can also leverage the microgravity environment to perform some modeling of fluid, thermal, and interfacial phenomena and extract few physical constants and perform some tests in space that help you improve products back on Earth. The low Earth orbit is also a unique vantage point where you can do technology demonstration, hardware testing for remote sensors, as well as testing of technologies that are aimed at space exploration, like in-space assembly and orbital service. The extreme environment of space can be used to simulate some of the extreme environments back on Earth, like the summer. You can do thermal cycling on the exterior of the space station, polymer degradation, accelerated aging of materials. So there's some ways in which you can take advantage of that as well. So in summary, there are three ways in which you can look at in-space manufacturing and research for both Earth and space applications. You can use the environment of space to create products in space and then bring them back to Earth for Earth applications. You can use the environment of space to do research, obtain data and knowledge, and then use that to improve processes back on Earth. You can use the space environment to design and do technology demonstrations to see the future of space exploration and developing the in-space economy. I'll be focusing, there's a lot that is talked about the third part, which is, future of space exploration, but there's very less focus that is on the first two, which is creating value back on Earth. This is a very important focus for Axiom Space and companies like Axiom Space, because that is the near-term markets for space manufacturing. So it is very important that we focus on this in addition to focusing on the space exploration side as well. So today I'll be highlighting a few applications on the Earth application side. In space manufacturing, or rather low gravity manufacturing, is not a very new concept. Historically, this has been seen in, for example, short towers, which were used to make nearly spherical lead shots for firearms in the 19th century. What was done here is molten lead was poured onto a porous plate at the top of a tall tower, and then the molten balls of lead fall down through the tower and into a pool of water. Now, during this fall, it experiences this low gravity environment or microgravity, where surface tension forces dominate and allow this, the balls to become nearly spherical in shape. So the way we see in space manufacturing is that the advantages in microgravity directly translates into changes in materials processes. Understanding this is the critical part. So understanding how microgravity affects materials processes like crystal growth, thin film deposition, self-assembly, solidification, helps us in developing new materials or improving materials that are currently being produced on Earth. And then eventually that will lead to applications back on Earth, and in space manufacturing will be a sustainable model. So I'll talk through a few examples today. One of the main obvious examples is how you can manipulate liquids in space. So the capillary length, which is the ratio of the surface tension forces to the gravitational forces, is about 1,000 times higher in microgravity. What this means is that you can make huge droplets in space. This is demonstrated very beautifully in the movie Passengers, where this swimming pool beads up into huge balls of water when the gravity is stopped. This means you can create large droplets and large liquid bridges in microgravity. And where this has been used is, for example, in the float zone method, which is used to grow high purity semiconductor crystals in Earth. But the size of the crystal is limited by the size of the liquid bridge that can be formed. But when you take this to space, form large liquid bridges and hence grow large crystals in space. Another advantage of space is that it's a convection-free environment. So even if there are density differences in the fluid, due to thermal or concentration gradients, you don't have any convection. So here you can use that environment to achieve purely diffusion-driven processes. You can also alter the grain growth in solidification processes. It obviously changes heat and mass transfer characteristics, and you can use it to isolate and study non-gravitational forces like Marangoni forces. This picture on the right shows a crystal that is being grown on Earth, and you can see this micro convection currents around it that affects how the crystal is grown. Also, the solidification interface in alloys and crystals is affected where you have the dendritic growth, and the dendrites can bend due to convection. They can also break and settle down the alloy, and so all of these cause defects in the alloy crystal. So some of the applications which we are exploring is protein crystallization, zeolites, industrial crystals, where you can grow large and diffractory crystals in space. And something I want to highlight is on the right, for the industrial crystals, all the examples that I've cited are from commercial companies. These are companies that are exploring growing industrial crystals in space for Earth applications. Semiconductor crystal growth is another big area where, especially using the gradient freeze method, there has been some studies that show that you have more uniform concentration distribution of the alloy material across the crystal, and you also have a more flat interface compared to those crystals that are grown on Earth. So this can improve the yield of the semiconductor that is grown in space. Not only can you grow crystals, but you can also heal crystal wafers that are already created back on Earth. So there's an example where silicon carbide wafers were flown on parabolic flights and thermally annealed under microgravity conditions to remove defects, and they proved that there was a statistically significant difference between pre-processed wafers and post-processed wafers. And I've only shown you a few examples. There are multiple other areas like organic frameworks, high entropy alloys, polymers, perovskites, which are yet to be explored in space. Lack of buoyancy forces is another advantage of space. So when you have density differences between particles or bubbles in the fluid, you don't have sedimentation or flotation. You also don't have a pressure gradient within the fluid. So this can be used for soft materials which can collapse under their own pressure. Some of the ways in which this has been leveraged is for improving colloidal products. P&G, for example, did a study in space where they were able to isolate the effects of phase separation and coarsening. So when the particles or oil droplets come together, on Earth, they start settling down even before you can study how the particles interact with each other. In space, you can isolate those two effects and try to model the phenomena better, which helps in improving shelf life of these products. Graphene aerogels is another area where there's some exploration from Stanford University. There is a step in the creation of graphene aerogels where they create a gel from an aqueous dispersion of graphene oxide flakes. And when the gel is being created, there is sedimentation, and so there's a gradient in the properties of the graphene aerogel when it's created. So when you go to space, you can get more uniform aerogels. Sorry. Electrodeposition is another area where you have a solutal concentration gradients, and that is expected to create some dendrite growth near the interface. So when you go to space, there is some expectation that you can minimize and make this thin film deposition more uniform. Layer by layer self-assembly is a method where you can self-assemble macromolecules or nanoparticles onto a surface. One of the ways microgravity is helping this is that there's a company called Lambda Vision, for example, that is assembling bacteria rhodopsin protein for making artificial retina. Now, these protein particles are huge particles, about in the micron scale. So they tend to settle down in the solution, and instead of coating the retinal thin film, they tend to settle down and cause non-uniform deposition. So what this company is doing is exploring creating these space so that you don't have the settling problem and you improve the quality of the coatings. So this is a real application where there is a small a high value product, a small mass, which has some real near term commercialization opportunity. Containerless processing is another area where which is only possible in microgravity environment, and it's very unique. You can grow, form, and reshape materials in space using different forces. And then another advantage is that many materials which are very sensitive to the contact with the crucible, if you solidify them without the contact, you can get more perfect structures, crystalline structures. You can promote reactions in bulk than promoting them at the surface. And then you can also use it for research in the sense that you can observe processes in the bulk without being obstructed by the container. Some of the places where this is being used is, for example, development of bulk metallic glasses or glassy metals. These are nothing but metal, usually have a crystalline structure, but a new type of metal was discovered called bulk metallic glasses, which have a amorphous structure. And part of this discovery and development happened in the microgravity environment because they are very sensitive. Nucleation of crystals is very sensitive to contact with the crucible. So they use the microgravity environment for initially developing these materials. And then the ZBLAM optical fibers is another big area in space manufacturing, and multiple companies are exploring this, where they've found that it is advantageous to draw optical fibers, especially heavy metal fluoride optical fibers in space, because the nucleation of small defects is prevented due to lack of convection. We can use the containerless processing, as I mentioned, to measure some thermophysical properties of high temperature melts. This is a furnace that is currently on the JAXA side of the ISS, where you can measure the density, viscosity, and surface tension of high temperature melts, and that can be used to improve processes back on Earth. And some of the areas that are very new and still being explored is 3D printing. And this is not 3D printing just for in-space applications. This is about doing printing in space and using the unique advantage of the microgravity environment to create supportless structures, printing composite materials. And because the heat transfer characteristics are different, you'll have different solidification in microgravity. And the bioprinting side has even more advantages because you can use low viscosity inks and you can build scaffold-free structures. So this is an active area as well. The final thing is I wanted to talk about is, again, highlight the extreme environment of space. So the outside of the space station has extreme vacuum, atomic oxygen, ionizing space radiation, extreme temperatures, high-speed micrometeoroids, and UV radiation. So all of these effects are combined. It's a very harsh environment to test materials, not just for space applications, but it's also can be used for accelerated aging, and then you can use it to model processes materials back on Earth. So as a summary, I hope I showed you some of the ways in which microgravity affects materials processes, and which in turn lead to in-space manufacturing applications. But this is just the tip of the iceberg. There's a lot of research that needs to be done to prove some of these cases and take them all the way to in-space manufacturing. So that's where researchers and innovators like you come in, bring in your ideas, and your research eventually leads to business applications in space. Axiom is already starting seeding some of these in-space manufacturing applications. We are working with, for example, United Semiconductors, a leader in making semiconductor crystals for making semi-metal semiconductor composite bulk crystals in space. So this is the picture here is an example of a defective crystal on the left and a perfect crystal on the right. So they can create the perfect crystal on the on Earth as well, but then due to convection, most of the crystals they produce are defective. So they have issues with yield, which we hope to improve when you go to space. And on the right, you can see a company called Flawless Photonics, who we are working with to develop some heavy metal fluoride glass processing capability in space as well. And besides this, there are a few life science applications that we're working on, which have been highlighted in this talk. But those life sciences is also another big area for space application in space manufacturing. Axiom is building the orbital lab, as I mentioned in the beginning, to enable this research and manufacturing in space by the year 2028. We plan to have modular and plug-and-play interfaces, which are much easier to integrate than the current ISS hardware. And then we also plan to have state-of-the-art characterization facilities so that you can do in situ iteration of your experiments in space. Currently, the experiments have to be flown. You develop a material, you bring it back, you characterize them back on Earth. And so this kind of is a huge long cycle for materials development. We want to shorten that cycle by having in situ characterization on orbit. Obviously, we'll have some utilities that will be provided for this research and launch and return services. And finally, because our station is going to be human rated, we would have crew time for doing these experiments. So although automation is the way to go eventually in the future, in the beginning, it is helpful to have the crew time to develop some of these applications and tune the experiments in situ. Besides the in-space manufacturing for Earth, there is the whole aspect of in-space manufacturing and logistics for space applications. By 2027, we plan to have about 8 humans living on the Axiom space station. But we are planning to expand that, about double the number of humans every 5 years and reach about 100 humans living in the low Earth orbit by 2040. So this is a very grand goal, and this means that there has to be enormous scaling of the services that are offered in the low Earth orbit. Right from you need power production, you need tools to process the materials and the methods to create food in space. Processing chemicals in space, and then data communication and processing for the humans present in space and between Earth and space. And of course, like in space, assembly of structures is a big area that we are looking at as well. One of the interesting example that I wanted to talk about in situ resource utilization is that the carbon dioxide that is exhaled by the astronauts is currently converted into methane and water using the Sabatier process. That methane is currently just released into space on the ISS. Axiom plans to capture that methane and then resell it for example, fuel applications on orbit. And this is some of the materials that we already have on orbit for good purposes. I'd like to conclude with a few thoughts on why this is the right time for companies and academics to be entering in space manufacturing, to be thinking about in space manufacturing. So we, as I mentioned, Axiom is working towards increasing human presence in space. So we're already sending private astronaut missions, working on professional astronaut missions. What this means is that as the number of humans in space increase, there'll be a surge in demand for launch and return services. And then that would in reducing the launch costs even further. There's already been exponential reduction of launch costs during the new space era over the last 20 years, but we expect that to go down even further, which will open up a lot of business opportunities that were not possible before. So currently, the limitation for in-space manufacturing for Earth application is the launch cost. So eventually, as that comes down, it'll open up a lot of business opportunities, and we can use space to solve Earth challenges as well. We are leading in the game by seeding some of those applications, and it is important to start developing right now so that we are ready when those launch costs come down to the right, and we hit the time when those business cases make sense. So in order to enable a space-based economy, we believe that it is necessary to grow and sustain human presence in the low Earth orbit and make it commonplace to sustainably live and work in space. So this is what we are doing through the private astronaut missions, professional astronaut missions, and building the Axiom space station. We also believe that it's important to incubate, accelerate, and operationalize new markets, products, and services, both space to Earth and space to space. And that's what the in-space manufacturing team and the infrastructure and logistics team at Axiom Space is focusing on. And so we believe that all of these activities will eventually lay the long-term foundation to building cities in space, which is our grand vision. So the sky is not the limit anymore. It is time to reimagine the possibilities without gravity and convert those ideas into reality. I thank you very much for your time, and I'm looking forward to your questions. Thank you very much.
Great. Thanks a lot, Divya. I think a virtual clap of hands is probably due for your talk. But yeah, this is exciting times. I think what you guys are doing at Axiom Space is wonderful. I now welcome questions. But the audience, either you can unmute yourself and ask, or you can type in the chat box and one of us will read it out for you. There's one question from GK, my colleague here. He's asking if you can elaborate a little bit more about what Axiom is planning in the life sciences area.
Okay, so life sciences, there are a couple of areas. So regenerative medicine, so there is, you can grow tissues in space, because of the microgravity environment, proliferate in a very different way. As I mentioned, because you don't have the crushing forces of gravity, these are soft materials, so the three-dimensional growth of cells is kind of supported in microgravity. So that's one area. Then the stem cell, there's an initiative on stem cells as well. This I'm not fully familiar with, but that's an area that is going on. And then the 3 bioprinting I mentioned. Then there's one more I forgot. Using because the bones age faster in space. You can use muscles age faster in space. You can use the microgravity environment to do some disease modeling, right? So you can accelerate the modeling of diseases in space. Some of those diseases where you have muscle atrophy, for example, and then use that knowledge to develop drugs back on Earth. So that's some of the areas that I think I can highlight right now. I can, again, if you get in touch with me, I can again give more areas and talk more about it as well.
Sure, thanks, Divya. I think GK and I probably will contact you a little bit later as well. I see a hand. Yeah, sorry, Arvind. Yeah, go ahead.
Yeah, hi Divya. Nice talk. I just wanted to know how does the ambient vibration due to station keeping activities like docking or trajectory corrections affect, how's that affect on the microgravity experience? How's that taken care of? Like when you are doing
it's been a problem. Not a very big problem, but it is something that we are aware of, and as we are designing the station, we are taking care on that side. So some of the things that we are doing is innovating both on the For example, one of the problem that we face is the exercise equipment of the human astronauts. As they are exercising, that can create vibrations, and we are kind of changing those configurations of those equipment so that that effect doesn't happen as much. Obviously, like isolating their quarters from where the research is going to be based, which will be a separate module. That helps a little bit. In terms of docking and those as well, I'm not like completely familiar with all the engineering aspects of the station, but I'm sure there's some innovation going on that side as well. We know that it's a big problem, and it is important for us to address it if we need to make these markets. So I'm sure these are being addressed.
But sorry, just to follow up on Arvind's comment, isolating vibrations is something we do very well on Earth as well. So I'm assuming there'll be much more. I mean, it'll be only easier upon space, perhaps, to isolate vibrations. I'm assuming
the vibration happens due to whenever there is an orbit correction or some of the capsule docks into the station. So that time you will not be able to do the microgravity.
Yeah.
Sure,
yeah. I think having the right isolating features for both the research as well as changing the ways in which that docking happens is probably some things that we are looking at.
Okay. Yeah, I see a hand up from Grishma Girija. Yeah, you can ask your question now, please.
Yeah, hi. First of all, Dr. Divya, thank you so very much for the very interesting talk. I have two questions for you. One is, since you mentioned there are a lot of commercial companies who approach for the different experiments in space, and the microgravity affects the properties of these materials. So how does the difference in these properties affect the technology transfer from the experiments in space to, with their applications, the commercial applications down on Earth? That would be the first question.
So is your question, so once the research is proven, your question is how the commercialization happens with those companies, is that correct?
Yes, since the properties are different from how they were performing above in the space.
Right. So some of these are like still early stage, so we are still proving those cases. There are a few that have been proven, but I will tell you this. So the way we imagine is Axiom Space is a builder, like we imagine ourselves as the infrastructure provider in space, right, and logistics provider in space. The companies that are working with us are the actual materials or life science experts, right? They know their technology the best. So what we are doing is we're developing partnerships with those companies. So they develop their Earth process, right? There will be a part of it which will go to space and then come back. You basically send the material to space at some point during their process, then bring back that material after it's developed, and then they continue their process back on Earth, then sell it to their markets on Earth. So it's kind of like a step in their manufacturing process is how we look at it. Obviously, it's not as simple as that, but then we, for example, in my life sciences, for example, it's more complicated because you have to have CGMP, rating, FDA approvals and all that. So that kind of increases the timeline and complexity of these projects. But we are working through those hurdles as well. I'm not sure if I answered your question fully, but let me know if I can.
Yes, you have actually. So I have one more question. A lot of the processes that you mentioned are those that require like clean room facilities and very controlled environment here on Earth, right? So the different environment up there in space, do they make the process easier, or do they actually make it more difficult for the manufacturing and the different control of environment that is required?
Got it. So for control environment like clean room and the other like bio-rated facilities, that's something that is an engineering problem. That's not like space is not going to limit that. It's just about engineering that into the station facilities and making sure we can meet the needs of the customers. And obviously, we are evaluating that on a case-by-case basis. We don't start right away by putting everything in place. We need to have a good business case to develop like change the station itself for that. Eventually, once we have proved the concept, so initially we'll have micro gravity glove boxes and stuff like that, where you have those control environments. But eventually, when the proof of concept is done, we can even build a module that is completely like clean room module for that application, if it makes sense from a business perspective.
Yes, understood. Thank you so very much.
Yeah.
Maybe I'll ask a question, Divya.
Yeah.
So if an academic institution or a commercial company has to work with Axiom, what is involved in that? I mean, do we just come and sit and talk with you guys and figure out how best we can use your facility? Is that what it is, or what sort of you're the business development manager, so I'm sure you have some kind of a different modalities of working with different people, right? So maybe you can just elaborate.
No, that's a good question. So we, you're right. Like, so first of all, like, it's not, processes are not like completely set in stone. We are very flexible in how we are working with the different partners. It really depends on what they want, right? But roughly, I would put it into two categories. Sometimes people just don't want to do one-time experiment in space, and like they're not yet sure if they're doing a long-term thing. So in that case, okay, we'll sit down, have some talks about, okay, this is your experiment. You want to, this is how much it would cost to fly to space. In the like for example, like developing that experiment for space, as well as like doing the on-orbit operations, bringing it back, and we just have a discussion on all that and see how we can obtain funding for that and stuff like that. But then the more important types of partnerships that we are working on and is the long-term partnerships, where we, as you can see, some of these are not, it's not one-time thing. We really need to do repeated experiments to prove the case and eventually lead to in-space manufacturing. So we're looking for a long-term partnership where, we bring in something like Axiom brings the space expertise, they bring in some in-kind contribution, we come together, create a model that works for a few years, and then we try to pursue these very challenging like applications. So I think there is like multiple ways in which we can work, and for academic institutions especially, we are looking for ways in which, for example, I mentioned we need to have state-of-the-art characterization facilities on orbit, right? And we are not the experts in these characterization facilities for materials and that. So what we need is somebody to be owner of those facilities. So those can be academic institutions. So imagine a on orbit that is owned by for IIT Madras, for example. So that's something that you can imagine for academic institutions. So in addition to them doing the research, they can also be the center point for other institutions who want to do research in space.
Okay, got it. Thanks, Divya.
Yeah.
So I think Vaibhav has raised a hand. Vaibhav, good job. Yeah, you can ask your question now.
Hello, ma'am.
Yes, hi.
Yeah, thank you, ma'am, for your nice talk. So as I just wanted to ask some suggestions, because I'm just starting my PhD at IIT Madras in applied mechanics. So I wanted to know how a student like me who's starting just a research career here, how he can contribute in a research oriented in a space domain, in materials and smart materials like that. Advice.
Okay, yeah, I mean, this is great. Like, I know it's really great to see students that are going towards in-space research and manufacturing. Previously, this has been like very hindered because of the timelines involved, right? It takes like 3 to 5 years very easily for an experiment to be flown and to be brought back, and that's the PhD timeline, right? So it becomes very challenging, but now it's becoming more feasible, so it's more easier for students like you to take it up. I mean, I don't have like specific advice other than saying, like, the field is open, right? Like it's really, there is a lot of opportunity that has not been explored. I showed you some areas where there's like zero research literally, but there is potential. So looking at those areas, looking at it from the fundamentals point of view, I always look at fundamentals. I don't believe in just trying out for some, like just because it's cool or anything like that, but it should be having some kind of technical rationale, right? Like why do this in space? And ideally, it should also have some kind of application that you're leading towards, because there are different ways in which you can investigate things, different properties you can investigate in space. So you, whether you're leading that towards manufacturing or just understanding fundamental phenomena. So depending on that, you can tune that research accordingly. I think like ExTeM is a great community. I'm really glad to see that at IIT Madras, and being part of that community is really helpful, because there's a lot of things that need to be learned from previous experiments in space, because this is a developing field, a lot of mistakes have been made, and we want to make sure that it's not made in the future.
Thank you, ma'am.
Maybe one more question, Divya. I know this is, I mean, Axiom Space is focusing more on low Earth orbits, and you guys are building platforms on that. But do you see long-term going towards, I know that there's been plans of settlement in Mars and moons and stuff like that. So do you see your modules floating around Mars and Moon as well? Because that's also part of the habitation plan long-term looks like for...
Absolutely. I mean, our goal is to be able to enable humans to become multiplanetary species. And the way why we are focusing on low Earth orbit is because that's the near-term commercialization opportunity. Moon and Mars are right now in the very exploratory stage, where only governments will be able to do that at this point. But eventually, yes, we will be able to reach a point where that will become a reality as well. But already there are companies that are looking at this asteroid mining and mining things on the moon and generating power on moon. So we have in talks with a few of them, but it's not our active area for the next few years, at least. Maybe like 10 years down the line, we will start like actively pursuing some of those.
Sure. Okay. Also, maybe one more comment on, I mean, there's, this, as I say, we are entering the space 2.0 era, 2.0 compared to what 1.0 was. And there's a lot of people who are now trying to launch rockets and stuff like that. So is there any issue related to sustainability that we should focus on? I know, there's been some concern also about, I mean, yeah, we're trying to leave the Earth and doing some stuff, but in the process, are we going to create more pollution on the Earth itself, for example? Is that something that is in your, sort of thought process as well, or is it too early now? Yeah.
It's no, it's never too early. It's definitely a big climate change is real. We believe that, and we need to be responsible. Right now, so I would say this, right? We were asked this question by another like energy company that was interested in working in space as well. So they mentioned one aspect, which is we're not yet sure like how much of these gases that are released contribute, like as it's going towards the space, the low Earth orbit, how much of that contributes to the greenhouse emissions, greenhouse effect, versus how much just goes into space. Like, I'm not sure about that contribution exactly, but that's something that needs to be understood. And then second is, of course, developing cleaner fuels like hydrogen or other fuels that can do the propulsion to space will be helpful, rather than using fossil fuel-based launch services. Those are the two areas that I can think of right away. I think we recognize it is a problem in addition to solving some of those, orbital debris and all that, which is also a sustainability issue in some sense. We need to look at this side of things as well.
Okay, sure. Thank you, Divya. Are there any other questions for Divya? Yeah, Salil, you want to go ahead?
Yeah. Thank you, Dr. Divya, for the nice talk. I have a quick question regarding, or rather a comment, I seek your comment actually, on the business case that you mentioned. So typically on Earth, when we talk about, say, new manufacturing approaches for getting new materials or new processes together, one of the common challenges is the scale. So how do you envision when you go to having, say, for example, the ZB-LAN optical fiber that you mentioned? So at what point of time does the defect-free formation versus with defect formation of Earth, try to get into a break-even point in terms of when you talk about the scale at manufacturing, how much length of ZB-LAN fiber you are manufacturing? So just wanted to get your comments on that or thoughts.
No, absolutely. This is the question that we're asked by most people. So this is important to make the commercial case, right? So let me address this point first. So scale, there's a scale aspect, and then there is also the cost of the economics aspect. So there's, for the scale aspect, we so initially we only have the orbital manufacturing lab, right? The research and manufacturing module, which will be up by 2027. This will support a number of different types of research, but not probably, like if there's a proven case, for example, ZB-LAN optical fiber, it won't support like full-scale manufacturing on that. So eventually we'll have to build a separate module just for that sake, so that you can get that particular scale. That's not a big challenge because we already have the expertise to build modules. It's just like basically replicating it, and we can connect it to our existing modules. The other, on the side of the economics, the way we evaluate cases is basically equating the launch cost, right? So what we do is, for example, what is the cost of making what is the value of the material per kg once you've made it in space? If that is comparable or at least like 3 to 4 times higher than the current launch cost per kg, so which is currently around 30K to 60K per kg if you have a human rated launch, but it's less than 5K if you have a non-human rated launch, right? So if you compare that cost versus the cost, the value of the material, then you can get a quick understanding of, hey, is this a valid business case or not? If not, then maybe we have to wait till that is achieved. That's just a quick test at this point we can use, but there are multiple other factors as well. As you know, there's manufacturing costs on orbit and all that. But eventually that would not be the biggest factor. It would be the launch cost that costs the most.
Okay, thank you.
Yeah.
Okay, any other questions for Dr. Divya? Okay, if not, again, thanks a lot, Divya. I know it's pretty early there for you for joining us and spending time to talk about the exciting developments in space. So yeah, I look forward to your visit sometime to Chennai and to our campus as well, and hope we can meet as well. So thank you again, Divya, for your talk. Thank you.
Thank you very much, Professor Bayer, for hosting, and thank you everyone for being on the call.
Thank you.